It's incredible that a scientist has discovered the first signs of life on the exoplanet K2-18b using the James Webb Space Telescope. The fascinating details of this study reveal for the first time what the living conditions on this distant world are really like. Large quantities of water and gases, which clearly originate from life forms on Earth, paint a crazy and fascinating picture of a distant world. Thanks to the precise analyses of the James Webb Telescope, it is as if we were studying an extraterrestrial biosystem up close for the first time. What did we really discover there, and what details shocked the scientists? The exoplanet K2-18b was discovered many years ago by the Hubble Space Telescope, but Hubble had its weaknesses. The old space telescope was unable to provide us with details about distant worlds. Now, with James Webb, a new era of exoplanet research has dawned, and for the first time, we have real data and evidence of what is really going on at K2-18b. Webb spectrometer analyses reveal every little detail. We know that this planet, 120 light-years from Earth, lies within the habitable zone of its star and that it's about 8.6 times the size of Earth. We also know that K2-18b has a hydrogen-rich atmosphere, which makes it a particularly interesting object for research. K2-18b is a Hycean world. This completely new category of exoplanets represents rich water worlds, and these planets may be far more suitable for life than our Earth. Predominantly covered by water, with tropical temperatures and perhaps some land masses, these planets could harbor an incredible diversity of life. For a long time, these ideas were just speculation, but now a scientist has proven that life can exist there. K2-18b has biomarkers discovered in the atmosphere. It sounds amazing. For the first time, we know for sure of a planet with so many biomarkers found in its environment that life on this world can be considered almost certain. James Webb spectrometer analyses showed evidence of methane. Methane is particularly interesting because it typically persists in atmospheres for no more than 2 to 3 years before it is broken down by solar radiation. This suggests that there is a source that continuously replenishes the methane in the atmosphere of K2-18b, which in turn raises the intriguing question of who or what is producing this methane. This gas is a biomarker because it is predominantly produced by living organisms on Earth. Living methane sources on Earth are mainly microorganisms. Methanogenic bacteria live in oxygen-free environments such as swamps, bogs, rice fields, and the gastrointestinal tract of ruminants. These bacteria decompose organic material in the absence of oxygen and produce methane as a byproduct. Termites also harbor methanogenic microorganisms in their digestive tracts, which produce methane as a byproduct of the digestion of wood and other plant materials. Cattle, sheep, goats, and other herbivorous animals, such as deer and camels, contribute to methane production through similar digestive processes. Other major sources of methane are wetlands such as swamps, bogs, and rice paddies. Anaerobic decomposition by methanogenic microorganisms that release methane also takes place in the sediments of lakes, rivers, and oceans, and there are probably large deposits of methane hydrate in deep ocean sediments. Methane is therefore a gas of life, and yet it does not necessarily have to be proof of life because, as we know, there are also large quantities of methane on Saturn's moon Titan, for example, which originates from liquid cycles. There, however, no evidence of life has yet been found. Compared to K2-18b, Titan is also a dark and cold world, and it lacks water. On K2-18b, water may even predominate, and methane seems to be only a byproduct. Another fascinating find was the potential discovery of dimethyl sulfide, or DMS for short, on K2-18b. This gas, which is toxic in large quantities, is produced on Earth by certain algae in the oceans. It's therefore another important biomarker, and whenever it appears together with water and methane, the probability of life is always greater. DMS is mainly produced on Earth by biological processes. The most important sources are marine phytoplankton species and certain algae. These algae produce dimethylsulfoniopropanate, which is broken down to DMS by decomposition processes involving bacteria. In coastal ecosystems, such as salt marshes and mangrove areas, microorganisms decompose organic material and release DMS in the process. Grasses in salt marshes have been found to emit DMS, and certain plants and mosses that grow in coastal regions also produce DMS. This shows very well how much the production of DMS on Earth depends on biological activities, and these processes almost always take place in coastal habitats. If DMS is found on a water planet, there is an obvious link to possible coastal habitats, plant growth, and at least the presence of simple organisms such as bacteria and microbes. In addition to these discoveries, Webb's analysis of K2-18b's atmosphere revealed an abundance of carbon dioxide and the complete absence of carbon monoxide, which also has interesting parallels to Earth's atmosphere. These chemical signatures could further indicate processes associated with biological activity on Earth, for example, photosynthesis, in which plants convert carbon dioxide into oxygen, respiration by microorganisms that release carbon dioxide, and methanogenesis, in which methanogens produce methane under anaerobic conditions, are typical of this type of gas evolution. The data from the James Webb Telescope also indicate that K2-18b has a thick hydrogen atmosphere. This type of environment favors water that is slightly warmer than on Earth and increases the possibility of life-friendly conditions. Real life on K2-18b, how will we succeed in detecting it? Wouldn't it be fantastic if we now had real evidence of life on this exoplanet? Proving life on K2-18b would be a monumental shift in our understanding of the universe, and scientists want to do just that. The first step would be to conduct further detailed spectroscopic analyses of K2-18b's atmosphere with the JWST, and we would need further technological innovations for the accurate detection of life. Initial analyses could help us to identify further and even more specific biosignatures, such as seasonal differences and movements in methane, oxygen, and DMS levels. We would have to use simulations to calculate which forms of life would fit the gas spectrum of K2-18b. To do this, it would be necessary to better study corresponding emissions on Earth and then determine suitable profiles. Computers could easily match these profiles with the gas combinations on K2-18b and give us possible scenarios and forms of life. In addition to spectroscopy, we could also use techniques such as transit photometry to study the chemical composition and dynamics of K2-18b's atmosphere. This method allows us to measure tiny changes in the star's light as the planet passes in front of it. Such data could provide further important clues to seasonal changes or climatic patterns, which in turn provide clues to biological activity. Further telescopes could be equipped with even finer sensors that can penetrate deeper into the atmosphere of water worlds like K2-18b and provide us with more data from the deeper layers. The JWST is already such an advance, and soon the extremely large telescope and the 30-meter telescope will be able to provide even more detailed data. In the future, our telescopes will continue to improve, and we can then hope for more and more details of distant worlds. Of course, the best way forward would be to develop space probes that could be sent directly to K2-18b. These probes could have advanced instruments on board to collect and analyze samples from the atmosphere and possibly the surface of the planet. These missions would take an extremely long time at a distance of 120 light-years. If we can one day accelerate probes to the speed of light or even faster than light, such missions would be conceivable. Until this is possible, we will only be able to simulate the environmental conditions of K2-18b in laboratories on Earth. By recreating the temperature, pressure, and chemical composition of the atmosphere, scientists can find out whether known terrestrial microorganisms could survive and possibly thrive under these conditions. Such experiments could give us further exciting clues as to what kinds of life exist on K2-18b and how they might have adapted to the environmental conditions there. Finally, the search for life in our own solar system will play a role in the coming decades. Probes equipped with drills will fly to the icy moons Enceladus and Europa, among others. There, the fully automated drilling systems will drill into the thick layers of ice for the first time and release floating probes with cameras into the ocean suspected to be there. If we find life in the universe on these moons for the first time, the probability that there are life forms on numerous exoplanets increases. Other exoplanets with evidence of life, K218b is by no means the only candidate that is currently in the spotlight of exoplanet research. There are numerous other exoplanets that are also promising for the search for extraterrestrial life. One of these exoplanets is TRAPPIST-1e, which lies in a system with 7 Earth-like planets. TRAPPIST-1e is located in the habitable zone of its cool dwarf star, which means that liquid water could exist on its surface. With its rocky nature and the potential existence of a dense atmosphere, TRAPPIST-1e will also soon be closely studied by the James Webb Space Telescope. If we find further biomarkers here, it would be a feast for the scientific community. Another main target in the search for life in distant star systems is the Kepler-186 system. Here, Kepler-186f in particular has aroused the interest of scientists. Kepler-186f is the first Earth-sized planet discovered in the habitable zone of another star. It has similar dimensions to Earth and could have liquid water on its surface. With LHS 1140b, we have another promising exoplanet that is located in the habitable zone of a red dwarf star. With its high density and potentially dense atmosphere, LHS 1140b would also be an opportunity to learn more about the habitability of planets in other star systems. That leaves Proxima Centauri b. The nearest Earth-like planet orbits a small and comparatively faint star. Proxima Centauri b is quite close to its star but still in the habitable zone. The planet was long considered the hottest candidate for a super-Earth in space, but then it was noticed that the star Proxima Centauri emits frequent and strong bursts of radiation in the direction of its planet, which may be very damaging to the planet. Despite these observations, researchers have not completely lost sight of this world. A special privately funded research project aims to send tiny nanocraft to this system just over 4 light-years away in the next 20 years. Then, for the first time, we could see real images of the surface of an exoplanet. Thank you for watching my video, and subscribe for the next upcoming space video with amazing information about space science.